Z-transform. Z-transform. We talk about a rational Z-transform. It's a rational format. Reason we are doing that because we want to deal with the linear time invariant system. It comes from a difference equation. We will see their connections in this lecture. And then afterwards, we were talking about inverse of Z-transform. Inversion of Z-transform is inverse Z-transform from the Z domain back to time domain. Once I do all these calculations in the Z domain, which is supposedly to be easier than working everything in the time domain, then you get a final result. I want to invert that back to the time domain and get me the time domain signal. Usually that's the impulse response Hn, which defines the system. And then we are using that to analyze the LTI system in the Z domain. And then we look at some of the properties, for example, the causality and the stability using the Z domain picture. So last time we looked at the rational function, xz can be written in this fractional form, bz over az, where each b or a is a polynomial of z, or polynomial of z to the power -1. And then we discuss about the zeros and the poles, especially the poles. The location of these poles can tell if my system is stable or not. So this is a picture of zero and a poles. So we end up here last time. We look at a signal. If the signal is causal, now I want to make sure that this is a precondition. Be careful, we are dealing with causal signals. If it's anti-causal signals, the properties will be exactly the opposite. But we look at a causal signal, xn, eventually we will move to a causal system, which is defined by Hn. So eventually we will use Hn to replace this guy. Eventually we were dealing with Hn. So Hn, if it's a causal system, so we have something to say about Hn. So here we are just using any general signal. So Xn, but make sure that we understand it is causal here. Okay. So last time we looked at if it's a causal signal, we have a pole within the unit circle. Within unit circle, meaning that I have a pole here, less than 1, then my signal will diminish. Eventually it goes to 0. So if you sum all these together, it's absolute summable. So my system is stable. My signal is stable in a way. Signal is absolute summable. I should not say stable. Stable we define to discuss about this edge. If the pole is on the unit circle or outside unit circle, then the signal is not going to diminishing. Either it's going over. This is an oscillation. This is just a sine wave. It's oscillation, or it diverges, become larger and larger. If I have a causal real signal with a double real pole, I have 2 poles, P1 and P2. So in the fractional term, it's being written like that. So xz in the Z transform, what I have here is I have this is on the denominator. I use that to calculate my poles. Again, how to calculate poles is this part equal to 0, right? Denominator equal to 0. At that time, xz becomes infinite. And then once you do that, that's 1 subtract AC -1 equal to 0. So 1 is equal to AZ to the power -1. Now, don't forget, this is inverse of Z. So you put in here Z equals to A. Right? In this case, because it's real, so I can simply put that Z equals to A. And that is a pole. That is a pole when you have Z at this point, because my denominator equal to 0, then xz, when z equals to a, it becomes infinite. So it's a pole. You drop into the pole. It's upward pole. You just the system busted. So with that, now again, because I'm doing the causal system, so that region of convergence is that is Z is greater than or equal to A. We look at this figure. If my two poles are within the unit circle, here it's multiplication, m equal to 2, because you have a square here, so we have 2. If it's within the unit circle, either it's positive or negative, then I have a signal. It's coming up, it's causal, so coming up from here, but eventually it will diminish into small number, close to 0. So it's coming up. This is, I have a phase, so it will have a 100 degrees phase, so boom, 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 jump like that. But eventually it will diminish in close to 0. Now, if we check if pole is equal to A, but A is equal to 1. So I have double pole exactly on the unit circle. This is 1, this is -1. And then my signal is actually diverged. It's not even keep at a constant value. It diverges. It diverges. Same thing. If I have two double poles outside unit circle, here A is greater than 1. Here A is less than -1. And then you can see the signal, it diverges. Actually, it diverges exponentially. It goes like that. See? So we still hold the fact that if the pulse is within the unit circle, then that's good. My signal will converge. It will converge to 0. It's diminishing. It becomes smaller and smaller. So it gives me a hope that if I'm adding those absolute values of those x in, I will have a finite number. The case of a causal signal with a pair of complex conjugate poles. Now, if I have two poles, a pair of poles, but they are complex numbers, then they have to appear as complex conjugate. So one is here, one is here. This is the same case when the pole is within the unit circle, which we just find out the P is actually equal to A, but it's less than 1 within the unit circle. And then I'll have this first picture. Let me ask you, why do I have to have a pair of complex conjugate poles? Meaning that if I got a P1 here, I have to have a P2 here. So if P1, for instance, I equal to alpha plus J beta, and then you can immediately tell me you got another pole at alpha subtract J beta, complex conjugate. That is because I have the parameters. They are real, right? This is only the preconditions. I have parameters of system. Parameters are those parameters. Here, this guy, and also we have a -1 here. We have a -1 parameter here. So collectively, we call those parameters, we call those an array of B. These parameters we call an array of A, A0, A1, A2. This is B0, B1, B2. Now in practice, all these parameters, because you need to build your system, and these parameters are real numbers. Now, how do you build a system? Well, system is when we have HZ, we will see later on. It's equal to BZ over AC. We will know when we do this, HZ equal to YZ over XZ equal to that. So from here equal to this, we will get YZ times AC equals to XZ times BZ. So what this means, well, all these Y's are the output of my signal. All these A's are the input of my signal, of my system. Input of my system, output of my system. So it can transfer back to the difference equation. And these parameters are exactly coefficients of my difference equation. That is, if you remember the block diagram of a system, something like that. It's my input coming in. I got output. Let's just using one feedback. You got a feedback, right? Feedback here. And this weight here is these are those parameters. This is the A parameters. So when you implement a system, you have to put some real numbers. Right? Therefore, all these A's and B's in practice, they are real numbers. That gives me that if this, you factorize that and find the P1 and the P2, and they have to be in conjugate pair format. Okay. It's coming from the real coefficients. So we back to here. Now, if I have a pair of complex conjugate poles which are on the unit circle, in this case, what we will have is we'll have signal like this. It is actually it's an oscillating signal. Now again, how do you see that? You can think that it's a sine wave, but the sine it's kind of rotate around a circle and going from left to right. Once they project onto this picture, the real axis picture, you get all these points. You get all these points. You can think that this is kind of 3D. It's kind of rotating out. And rotating out. The same, excuse me, not that fast. Not that fast. It's probably like this. This is kind of like this, rotating out. So, but once you project onto this real side, and you will see all these. But it's a kind of sine wave. It's going outwards. If my two poles are outside the unit circle, here P1, here P2, and then the signal Xn is it diverges. It becomes larger and larger, So we still have our conclusion that I need to have those poles strictly within the unit circle in order for me to have a signal Xn become smaller and smaller, and it will be able to sum all these together, absolute summable, and it give me a finite number. Okay, so we have some other case. If I have a double pair of poles on the unit circle, so I have P1, P2, P3, P4, it's also there. It's also diverges. So we do some other check. It's also on the unit circle. It's not good enough. I have to make sure it's inside the unit circle. So the impulse response of a causal linear system is a causal signal. So what does that mean? Now that we have already seen that before. What is a causal linear time invariant system? Is my system output only depends on the current input and the previous input, and possibly previous output. I can have a memory to store the previous output yn minus 1, yn minus 2, yn minus 3, but the current output does not depend on future input or future output. Of course, in reality, that's not possible. So it's causal. It's reasonable, right? It's causal system. And that is a causal system in practice. If you check with the impulse response, we already said the impulse response is a causal signal, meaning that Hn equal to 0 for all n less than 0, right? This is the mathematical form to check the causality of a system. So if a pole of a system is outside the unit circle, the impulse response of the system becomes unbounded, and consequently the system is unstable. So as we see all these pictures before, so now if I have here Z domain, this is unit circle, this real part, imaginary part. So I am looking at the Z domain. This is my Z domain, but I'm looking at HZ. If I have a pole outside unit circle, whether it's complex conjugate pair or somewhere here, then this guy HZ will become infinite. Let's say this is P1. So this is when I evaluate Z equals to P1. And then you give me a value which is infinite. So the system is unstable. And then I have to have all these poles within the unit circle. These are the good poles. Okay, and this pole. And then I can have a system that can be stable. Okay. What is the region of convergence of a causal system? Region of convergence of a causal system. Let's check back. Actually, it's here. So this is a step function is causal. This is a causal signal. This is a causal signal because I have un, right? Now this is anti-causal. This is a causal signal. So if I have a causal signal, my region of convergence is greater than something. If it's anti-causal, it is less than something, right? So what I understand is that if I have a causal system, the region of convergence is outside a circle. These are the region of convergence. And if I have a pole, C equal to P1, let's say. Where do you see this pole landed in this picture? So I have a causal system. Therefore, I know my region of convergence is outside this range. So you will have, if I have a causal signal, this is causal. Either way, I have a causal signal, then you have to be the exterior of a circle of R2, exterior of a circle. If I'm checking with the absolute value of this, if we are checking the stability, remember last time, right? Checking the stability, I'm only looking at this guy, 0 to infinity. So as if I'm looking the second term here, but the R is equal to 1. All right, so let me say that again. So this is how we do with my system, right? It's a signal, xz. We bring that into two parts when we discuss about region of convergence, remember. And then we check with the second term. We say, well, this should be a finite number. Therefore, you get you should have the R is large enough. So we actually have this part is coming from here. So R should be greater than a certain value. And then if this is a causal, if I'm checking with stability, causal looking at this part, if it's stability, I'm looking at the absolute summable. So we have here the sum over the signal, or if it's causal system, then simply replace x with h. We want to make sure this is finite. So we kind of make this R equal to 1. In our case, we got a I is equal to 1. So we are checking with this region of convergence. We're checking with unit circle. R is equal to 1. This is the region of convergence for a causal system. Okay? Here is the unit circle. Now, in this case, when I have this R is particular 1, all I'm doing is I'm actually evaluate all these things on this unit circle. So these are the value what I will get to check with this guy. So I'm working on the unit circle. And in another word, I want to take all these z's. I want to check with the unit circle. That is equal to, when this R equal to 1, that is equal to 1. I want to see when I'm taking the z values, when the absolute value of z is equal to 1, I'm checking the unit circle to see if all these values will give me a stable output, will give me a stable capital X or capital H. Okay. In other words, I want to kind of pick up the z values around here. And I want to make sure all these, when you pick up a z here, then hz or xz in this case is finite. Is finite. Therefore, this unit circle should be in the region of convergence. Now, if I'm checking with this one, when I'm dealing with stability, I'm actually checking with that. Right? So this R is 1. So I am going to pick up all these points of z points on the z plane, that all these points have this z absolute value equal to 1. So I am just picking the particular z points on the unit circle. And I want to make sure the unit circle as z, that will give me an hz is finite. So the value evaluated on the unit circle will give me a stable output or stable system. We look at the picture here on the left. So we got a causal system. Causal system, the region of convergence is exterior of a circle, any arbitrary circle. This circle is actually radius of A, let's say. Well, it comes back to what's the definition of region of convergence, right? What does that mean, region of convergence? Well, you need to have a converged output. The hz should be finite. Therefore, this you evaluate on the unit circle. The unit circle should be that. in the region of convergence. So erase that internal, it won't be this one and it won't be this guy. It is the red one that we have here. So my unit circle is in the region of convergence, which in my case is a causal system. Causal system is region of convergence exterior of a circle. So it should give you like that. So the exterior, it's somewhere here. That's in the shaded region. That's region of convergence. Now, where are the poles? Poles, let's just say one pole, a real pole, P1. Is the pole here, or here, or here, or here? By definition, what is a pole? Pole means that HP1, if you evaluate Z at this value of P, and then this guy becomes infinitely large, right? You drop into a pole, it becomes infinitely large. The pole is not in the region of convergence. Well, if it's in the region of convergence, that's just finite. It's not a definition of a pole. Therefore, this is my pole look like. It should not be in the region of convergence. So it will not be here. It's not here, not here. And the pole has to be inside here. This is P. Therefore, from this picture, now you know exactly this green point, P pole, should be strictly within the unit circle, which is the red circle, right? The red circle is the unit circle. Therefore, give us conclusion. If I have a causal system, make it stable, I have to make all these poles within the unit circle. Now let's look at how to use those fractional Z-domain format to help us solving for linear time invariant system. So I have a linear time invariant system which give me a convolution. So I got a system, input xn, system identified by the impulse response, and the output is yn. So we got this convolution. In the Z domain, convolution becomes a multiplication. So it's simpler. That is yc equal to hc times xc. And if we know the input, we observe the output of system, we can determine the unit sample response by first solving hc from this. Right? This is a multiplication. Therefore, you do division is very simple. Hz equal to yz over xc. And once you find the hz, then we can do an inverse Z transform. And from here, we do an inverse Z transform and then get back to Hn. We find the system. We find the impulse response of the system. And here, we usually call this Hz the system function or the system response. How we can use that to solving for our linear time invariant system? Particularly, how can we relate a Z-domain expression, a fractional Z-domain expression, to a difference equation? We know a LTI system is described by a linear constant coefficient difference equation, like this, the first line. So we have here the parameters A's, parameters B's, and all these A's are working on Y, the B's are working on X. And that's by conventionally, A's is with the output, B's are with the input. We have seen this difference equation a lot before. And if you move everything to the left with Y, all the Y's to the left, so we have sum Yn minus K, A, K from 0 to N, where A0 is defined as 1, equal to the sum of the input K from 0 to M, B sub case, X n minus K. That's what we define a system, right? Using difference equation. In this case, every Y is to the left, every X to the right. A's and the B's, those are the constant coefficient. And it can be real number, it can be complex number. Once you get the parameters A's, you define the system. How to implement the system? Well, we are using this block diagram. Last time we see that if Xn, you got a delay, you got Xn minus 1, then you multiply by B1, right? And you got another delay, you multiply by B2. Let me just take those two. And so we adding together. And then you output, well, you cannot draw here, but you output a yn, and then you do some feedback. Similarly, you have this, you're putting all the weights A's and the feedback. That's how we implement a system. We need to have all these weights, A's and the B's. Okay. Now let's look at the system function in the Z domain. So I do a Z transform on both sides of my equation. So yn simply becomes yz, very simple. Because Z domain is a linear operation, so I can work on each individual terms. I have a Z domain, I have a Z transform on the entire thing, but I can bring two pieces. So we have a negative sum. This is a constant, so bring it out of Z domain of the Z transform. So A sub case. And then in here, what I did is I am doing a Z transform on yn minus k. Okay. So what that will give me is I have yc times z to the power negative k. This is the time delay property or time shifting property of Z transform, right? You have a time delay in the time domain of k. In Z domain, you just multiply by Z to the power negative k. Okay, so we have that. Similarly, we work on the second part. So we have all these input x. So we take a constant bk as well. And then this is xn minus k transferred to Z domain becomes xz times z to the power negative k. Okay, so it's because it's linear, it's very easy to do that. And then similarly, we put all these y's to the left of my equation. X leave at the right side of my equation. So we got that. Now, then because I have a yz here, I got a yz here as well. You just multiply by z to the power negative k. So it's very easy for me to take out, to pull this y out of this, this entire combination. So yz times 1 plus, and then we have sum all these parameters times z to the power negative k. Now this term z to the power of negative k due to the delay here. So we put in here. Similarly, we got xz on the right side, xz times this combination of all these sum of b sub k times z to the power negative k. Because I have yz here, xz here, very easily, I can bring this xz to the left of my equation. So it become yz divided by xz, and then bring this term to the right of my equation. So it becomes that fraction. So it's a fractional format. It's sum of bkz sum power negative k. Over here, that's 1 plus sum of ak c to the power negative k. All right. Now, what is this? This ratio, that's good. That's our system response. That's exactly what we want. We want xz. It's a division, very simple. And this system, it's given by this fractional format, where on the numerator, it's a polynomial. On the denominator, it's a polynomial. It's a polynomial of 1 over z. So that gives us a very nice bridge. We actually connect these two. Why we like a fractional expression? Because it completely comes from my difference equation. This is my difference equation. Now, the difference equation is to describe a linear time invariant system. We know that already. And all these parameters, A's and the B's, are exactly the parameters here, A's and the B's. We're using that to find HZ. And using capital HZ, using capital HZ, we know we can very quickly find HN. That is doing the inverse Z transform. Okay. Once we got HN, we can say, well, I solved the problem. I find your system. I find your system. Now compare with my original difference equation. If I give you that, I told you now I observe some output. I know my input. I want you to find the system, identify the system HN. Well, that's kind of difficult to do, right? It's involved. How do you do that? You need to solve for this difference equation. Now, given A's and B's, you still need to find Hn. Well, Hn is a deconvolution of y and x. It's very difficult to do. So we kind of circumvent this problem and go through the Z domain. So it's very simple. We put in like that. Find Hz, and then to identify the system of Hn. Okay, and next time we will look into some details on putting some numbers to see how we actually solve the problems like that.